Static equilibrium. What was equilibrium when we studied translational motion? Well, it meant that all the forces were balanced and the object wasn't accelerating. Otherwise known as the net force was equal to 0. So what do we think equilibrium is in rotational motion? Well, our analog for force is now torque, so it makes sense that equilibrium in rotation is when net torque is 0. What does the word static mean? In physics, static means that it's not moving. So when you put these three things together and we talk about static equilibrium, there are three conditions that have to be met for an object to be said to be at static equilibrium. The first is the net force acting on the object must equal 0. This is in all directions, so both in the x direction, the y direction. If it's three-dimensional, it needs to be in the z dimension as well. We won't do that in this class, but do know that in real life, things are in 3D. The net torque has to also equal 0, and this is about all possible pivot points. And because it's static equilibrium, the object and system need to not be moving. An example of an object in static equilibrium is two children sitting on a seesaw, and you'll notice they are not at the same distance from the pivot point, okay? But the seesaw at this point in time is not moving because where they are has balanced each other out. You'll notice that the upward force at the pivot point, okay, has to be counteracted by the two downward forces to make your forces in the y equal to 0. So here's a sample AP problem. This is actually from a Physics C test in 2008, and I've taken out the couple of questions at the end that probably wouldn't apply to AP Physics 1. But you can see here that this is what a setup would look like, and having to draw and label forces acting on the rod and then calculate the reading in the spring scale is going to be something that we could do in this class. Okay. I love the OpenStax book because they put problem-solving strategies frequently throughout the book. This comes straight out of OpenStax, all right? And so if you want to go back and look for these instructions, these are in section 9.4, all right? So the first thing you want to do is look at whether or not you're solving a static equilibrium problem, okay? If the acceleration of the system is 0 and there is no net torque, then this is going to be true. Or the problem might say that the system's in static equilibrium, and so you have to solve for a particular variable to make that true. Okay? As always, you're going to start with drawing a free body diagram. However, since we're now looking at things with torque, where the forces are applied can be important. So you'll have to make sure you include the magnitude, direction, and the point of application for the forces acting on the system. Okay? The next thing you're going to do is look at your equations that you use in static equilibrium. This is where you're going to start to get numerical answers, okay? You have to use your equations. All right. If you're doing something with torque, and in this unit, you can guess that most of the time we will be, all right, you're going to have to figure out, all right, where your pivot point is. You may be able to choose one. Okay, if you do get to choose one, there are some places that are very helpful. Okay, so in the previous example of the seesaw, the only upward force was from the pivot point, and if it was at the center of the board, it meant that you could very easily figure out your y forces and your distances from the pivot point. So, again, if you have a choice, you want to cause any torque by an unknown force to be 0. So either at the pivot point or along a line through the pivot point where that sine theta in the equation is 0.